Hello, chemistry students. This is Dr. David Kreller of the Department of Chemistry of Chulalongkorn University in Bangkok, Thailand. I'm here with another video lecture. In this video, we're going to talk about Chapter 3 in the book Chemistry, authored by Raymond Chang and co-authored by Kenneth Goldsby. In this first video, we're going to talk about quantifying matter. And we're going to talk about how the most basic way we quantify matter in the real world is by mass. But as chemists, we want to connect mass to things like the moles of particles and the number of individual particles. And we will find ourselves defining various things like Avogadro's number and the moles as we talk about how mass is connected to these other quantities. Let's get started. You know that substances are quantified by mass in the everyday world. You know from going to the supermarket and buying food that food items are often quantified by mass. If you want to find out how much you're buying, determining if it's just the right quantity, you might weigh it. And also, those items will be weighed when the people at the supermarket determine how much to charge you for those quantities if you want to take them home. Also, you might quantify yourself by mass if you're interested in inspecting the quantity of yourself to determine whether maybe there's too much of you physically or not enough. The words mass and weight are sometimes used interchangeably. Obviously, weight is a force in a gravitational field, which is directly proportional to mass anyway. So really, I'm talking about mass in this video, but you know that mass and weight as methods of quantifying are used interchangeably. Okay, so anyway, in the chemistry lab, we also quantify substances by mass with pieces of equipment like shown here, these balances. But in chemistry, we want to know the number of particles in substances. So we ask ourselves, can mass be connected to numbers of particles? So to review this, mass is the most basic way of quantifying matter. We take some matter, we don't have a piece of equipment that we can use that can tell us automatically how many particles are there. But we know that matter is made up of individual atoms, and we know things like atoms combine in whole number ratios to make new substances. And there's things such as chemical reactions, and when the reactants in when the reactants in a reaction go away and products form, they do so in exact numerical proportions. So for the purposes of chemistry, it would be great if we could take this material that we've quantified by mass and connect that mass to number of particles, because the magic of chemistry can be seen, or we can understand chemistry in terms of numbers of particles. So that brings us to the contents of this first video. We will discuss the way that very thing is done, the way that mass is connected to number of particles. But we'll find ourselves needing to define Avogadro's number, the mole, and the mass unit of AMU, and ideas of what's meant by molar mass and what we mean also when we say things something like molecular mass. First, we will talk about Avogadro's number. It's a so-called counting word. It's pretty common to use counting words in English language for objects that quite regularly appear in units of 2, quantities of 2, and are bought and sold and handled in quantities of 2. We have a counting word pair, which means the word means a number, the number being 2. Okay, then for slightly smaller objects that are commonly bought and sold and used in units of 12, we have another counting word, a dozen, which means a number 12. And we take slightly smaller objects, pieces of paper, quite small in terms of their thickness. And so we quite often handle them in stacks of a certain number, stacks of 500. So we have the counting word ream, which means 500. So one ream will be a stack of those papers, piece of paper 500 thick. And then when we go to the store to buy paper for our copiers, for our printers, will buy many reams at a time. So Avogadro's number, as the name suggests, with number in there, it refers to a number. 6.0221367 times 10 to the power 23, huge number. And a number that huge is only useful when we're counting up or quantifying things that are made up of extremely tiny particles, like the atoms that make up matter, or the photons that atoms or molecules emit or absorb. So another concept that goes along with Avogadro's number is the concept of the mole. The mole is like a quantity of substance. It's kind of like a counting number, but it's like a counting number kind of inverted, in a strange way. When we say we have 1 mole of a substance, the substance of course being composed of very tiny individual particles. When we say we have a mole of that substance, that implies that we have Avogadro's number of those particles. Say for example, shown here is a sample of water, laboratory-sized sample of water. And if we actually have 1 mole of water, well, we understand that that water is made up of molecules. And to say we have 1 mole of it, we have Avogadro's number of molecules. Okay, so the word mole has a double meaning. Basically, we're talking about amount of substance, but specifically you need to understand that it refers to an amount of substance that corresponds to a specific number of particles. Avogadro's number of particles. So now let's look at some ways of seeing how big Avogadro's number actually is. And we'll start by repeating the fact that for anything but exceedingly small, the mole is an impracticably large amount. Imagine taking dot, or call it a period, that you make on a piece of paper just by pushing your pen or pencil against the paper. So do that. Reach down and make a dot. Okay, and then repeat that process, but don't put the second dot on top of the first dot. Put the second dot beside the first dot. Okay, so you're making a little line. Repeat that process, so you have done it 3 times. Put the third dot beside the first 2. Then do it again. Do it 4 times, 5 times, 6 times, 7 times, 8 times, 9 times, 10 times. You are making a line of dots. And if you were to repeat that process Avogadro's number of times, you would end up with an exceptionally long line of those dots. And in fact, if you took Avogadro's number of dots, that line would be so long, it would be approximately equal to the radius of the Milky Way galaxy. But you wouldn't live long enough to repeat that process Avogadro's number of times. Take a marble. You know how big a marble is? You can hold it in your hand, little thing. Take several to cover your hand. Well, imagine we took Avogadro's number of marbles and we placed them on top of the surface area of the United States. I used to live, this is an aside, me telling a little story. I used to live in the state of Georgia in the United States. Prior to that, I was living in the state of Indiana. Those are both pretty big states. So imagine taking either one of those states and covering the surface area of that state with marbles. That's already quite a large number of marbles needed to cover the state. But not only do I cover one state with marbles, I cover each and every state in the contiguous United States with marbles. And then, if I'm going to use up Avogadro's number of marbles, not only can I cover the United States, I can put them on top of each other several layers thick. And in fact, I get a stack of marbles 112 kilometers thick. That gives you some idea of how large Avogadro's number. Okay, that brings us to the end of the very first video as we discuss chapter 3. And what have we talked about here? To review, we've talked about mass as the basic way of quantifying matter, but the fact that we want to connect mass to moles and things like number of particles. So we found ourselves defining things like Avogadro's number and the moles as we find ways to connect mass to number of particles in chemistry. So in the next video, we're going to carry on and we're going to define some new mass units that are used at the submicroscopic level. The atomic mass unit will define also things like molar mass and molecular mass. So thank you for watching. See you in the next video.